For section 312, we're back to exponential equations, but we're going to solve those exponential equations graphically and algebraically. And to solve them algebraically, we're going to need to use logarithms to do that. So that's our tie-in to cluster 2, but we're certainly going to be mixing in clusters 1 and 2 as we work on these exponential equations. Okay, data set first, looking at the Hispanic population in years since 1970. So I went ahead and plotted my data in Desmos. Got to slide it over here. And let's zoom fit on that data set. Do we believe that this data is better modeled by a linear or exponential function? Okay, so I do see that there's a little bit of curve right here. If I'm not real sure, I could do both regressions. So y1 approximately mx1 plus b, and then I could do y1 approximately ab to the x1. And hopefully it's a little bit more clear here that linear does like decent, but it doesn't follow the curve of the data set the way exponential does. Ooh, exponential looks a lot better in terms of that little curve to the data set where it is increasing at an increasing rate. So goodbye linear. We're going to say the exponential is the right choice here because it's increasing at an increasing rate. Because we see the curve and we see that it's increasing at an increasing rate. And our data set is going to have that exponential curve to it and not be a straight line. All right, so then graph it. Sometimes we graph it already just to talk about it, but there we go. We graphed it. And write down the regression equation. So I checked my log mode box because I have to for an exponential equation if I want my parameters to be the same as they would be on any other device. So my model, P of t, as they have asked me to call it, is going to have a times b to the t. And my a value is 9 point, okay, a round to 2 places. They do this a lot here. They say to round a to 2 places and b to 3 places. You need more precision on your base than you do on your initial value. So we're going to have a different rounding requirement here. So a is 9.55. It looks like if I round to 2 places, 9.548 or 9.55. And my b value be 1.042 if we round to 2 places and then to the, or 3 places, I'm going to say, and then to the t. Okay, so graph visually, how does it look? Beautiful, because that automatically happens on Desmos, and we can see that we have a really nice R-squared value, 0.9944. So it's going to be a strong fit. Okay, so let's make a prediction. So first things, I got to rewrite my equation. P of t, and we said it was going to be 9.5 times 1.042 to the t. And we're trying to make a prediction in number 5 for the population in 2025. And we started our data in 1970, so we're going to be evaluating our function at 55. So P of 55, because 2025 minus 1970 is 55. Okay. So P of 55 gives us a population estimate of 91.78, and units, just million. So we're predicting the population in 2025 is 91.78 million Hispanic people. Okay, using our model, write the equation that can be used to determine the year in which the Hispanic population will first reach 75 million. So 75 is my output, so we're going to put 75 in place of our output, P of t. So 75 is equal to 9.55 times 1.042 to the t. Now we've done this before writing that as the output value, but then we've gone and graphed it and done y equals 75 and graphed it. Now I'm going to do that, but I'm also going to solve it by hand. So it's important that I have this set up correctly when I get to number 7, where I get to solve this equation by hand here. So that's the equation we're going to solve number 7, but first we'll go ahead and solve it graphically with an output of 75 million. We can see up here, let me turn off the regression line so I don't accidentally click on the wrong one there. And 50.94. So this ordered pair up here is going to be at 50.09. That's a big difference between 50.9 and 50.09. I misread that at first. And that's 50 years after 1970. So that puts us in 2020. Okay. So we would finish our answer within 2020. The Hispanic population was predicted to be 75 million. So the 50 isn't actually the number they're looking for. They're looking for the year, and so we would add on to our starting year to get the year for the prediction. Okay, that's the graphical version for how to solve. What we want next is the algebraic. So we have our equation equals 75. We're going to use the algebraic approach. So the first thing to do is to isolate the exponential factor by dividing both sides by the 9.55. So we're going to divide by 9.55 on both sides. So that's going to give us the 1.042 to the t is equal to, I've got to take 75 and divide it by 9.55. About 7.853. I'm going to keep an extra decimal place there because we'll round down to 2 places at our answer, but now we've got 3 for the mid steps. Okay, now there are 2 ways to solve this by hand. There's the way that they're directing us to do it, and then there's the way I prefer to do it, which is using the inverse function. So I'm going to switch to that, and I'll come back to their method, which is more of an older method, a traditional method, not my favorite. So I'm going to start and write this again over here. So 9.55 times 1.042 to the t equals 75. And again, the first step, no matter what method you're doing, is to divide both sides by 0.955. You got to do that. You got to get the exponential by itself. Okay, so the method that I'm going to show over here is going to be based on the inverse function. And it's using that b to the y equals x equivalency with the log base b of x equals y. And so we're going to switch this equation that is currently in exponential form into its inverse logarithmic form. So it's going to be starting with a logarithm that has the same base as the exponential. So logarithm base 1.042 of the argument of the logarithm is the answer to the exponential. So of 7.853 equals the answer to the logarithm is the power on the exponential. So I have a number here. This is all just a number equal to t. So I'm going to evaluate that number in Desmos. We're going to do a log with a base 1.042 of 7.853, and we get 50.09 equals t. 50.09 and so on. Okay, so 50.09 equals t. When we solved this equation up here graphically, That's the same thing that we got, right? 50.09, 50.094. I have one extra place up here. But I'm getting the same result algebraically that I got graphically right here. And so this also implies that my year is going to be 2020, in 2020, and so on. There were 75 million Hispanic people in the US. Okay. All right. So this is the inverses method. That's my favorite method to use in this situation, is to apply the inverse function. We'll go right on in. Now, this is a different method. This is the more traditional method. It would involve taking the log or the natural log of both sides. If I get to choose if I'm taking the log or the natural log of both sides, I usually go for natural log. You can decide if you would like log or natural log. I'm going to do natural log. So I'm going to take the natural log of both sides. Natural log of 1.042t equals natural log of 7.853. Now, the reason to take the natural log of both sides is to apply the property of logarithms that says that your power comes down as a coefficient. So if I use that property to remove the t as an exponent, that's going to be t times the natural log of 1.042 equals the natural log of 7.853. All right, and then if you're going to solve for t, you're going to divide natural log of 1.042 from both sides. And if I divide those two things, I should come out with t equals, and I need to take the natural log of 7.853 divided by the natural log of 1.042, and I get 50.09. So I'm getting the same answer 3 different ways, graphically and algebraically by inverses and algebraically by logging both sides. And again, this would give us the in 2020 start to our sentence. There were 75 million Hispanic people in the US. Okay. How does your answer to part D compare with it graphically? Same. And then we have to decide which of these two methods that we like. I want to share before I go on that it didn't matter if I natural logged both sides or if I logged both sides. If I logged both sides, I'd have log instead of ln in my division here. And again, same answer. So if you want to log both sides instead of ln both sides, go for it, because it's not going to affect your answer as long as you're doing the same logarithm to both sides. Okay, I like the inverses method. Up to you about which method you want to do. In class, I'll get to ask you and you'll tell me which one is your favorite. But if I get to choose, I'm going inverses. And today I get to choose, so. Huh. All right, so got some data. This is still about Hispanic population, but it's number of voters this time. Number of Hispanic voters, and we want to do years since 1992. So we're going to have 0 for 1992. We're going to have 4 for 1996. We're going to have 8. Then we're going to have 12 and 16 and 20 and 24 for our inputs. Let's get a table going. Okay. Come on, zoom fit. There we go. All right, so here's our data. And they want us to find an exponential model. They could have asked me, like they did in the last question, if I thought linear or exponential was going to be better. So this piece of it looks pretty linear, but if I did a linear with all of it, it's not going to fit too well. Exponential is characterized by slow growth followed by more rapid growth, and this slow area is maybe going to push it to exponential. So we're going to do what they've asked us to do and find an exponential model. Log mode on. Hey, it's pretty good, right? It's got a 0.966, and only this one is far away, and that was because there was no change in those two values, but the rest are pretty darn spot on, close to the model. So let's write our model down. They want us to call this model V. Just bumping my stuff here. V of t, A to 1 place, okay, and B to 3 places. So 3.9 for our A value, and if we want to round that to 1 place, and 1.053 if I'm going to round B to 3 places. Okay. Before I go to my next page, let me just type that model in here. Oops. All right, and let's see what the next page has. For our predictions. Okay, so use the exponential model to predict the number of Hispanic voters in 2020. So we were working in years since 1992. So we're going to need 2020 minus 1992. So that's going to be an input of 28 years. So we're looking at a prediction V of 28 there. And that gives us 16.56. I think it's million. Yep, million voters. Write the equation that can be used to predict in which year the number of Hispanic voters will first exceed 20 million. So it's 16.5 million in 2020. When will it exceed 20 million? Okay, so I have my equation shown right here. So I'm going to keep that on screen for just a moment. And 20 is going to be my output value. So I'm going to have 20 equals, and then 3.9 times 1.053 to the t. We're not going to solve it graphically first. We might do it afterwards just to check. We're going to solve it by hand algebraically. So the first thing that I need to do is to divide off the 3.9. Okay, so, well, I got to figure out what 20 divided by 3.9 is. 5.128 equals 1.053 to the t. Then I'm going to apply the inverse to switch this from exponential to logarithmic form. So I'm going to write a logarithm with the same base as the exponential, log base 1.053 of the answer to the exponential is the argument of the logarithm. And the answer to the logarithm is the power on the exponential. So now I can enter this into Desmos. Pull my book down a little bit so I can see both of those. A logarithm with the base 1.053 of 5.128 gives us 31.65. Okay, and so I'm going to add that to my starting year, which is 1992. We're going to add 32 to that, right? Because we'll just round it up to the nearest year. And so that's going to be 2024. They also want us to remember that, keep it in mind, the elections happen every 4 years. So had I not rounded up and said 2023, obviously it's not an election year. But 2024 is an election year, so we'd round to the nearest election year for this case. So we're going to predict that in 2024, there will be, what was it? 20 million. It will exceed 20 million, so there will be more than. I'm going to stick that in there. More than 20 million Hispanic voters. Now I can be sure that it's more than, not just 20 million, because really technically somewhere near the end of 2023, in 2023.65, there would have been exactly 20 million. So I've gone above that, and they wanted to know when I was going to exceed, be more than. So really I was looking for that more than 20 million statement. All right. Last one, we're not going to have to do regression to get the equation in this last one, but we're going to set up our equation of the form P equals P naught. That's how I read P sub 0. That is read as P naught, but the naught just stands for initial, so P naught times e to the negative kt. Okay, and we're going to use this formula. P naught is the initial amount, k is the continuous decay rate, capital P is the amount present at the end of t years. Okay, so looking down, there is an example up here if you want to look through how that they create their function and make their prediction in that example. We're going to jump down to number 9 right here. Talking about strontium-90, it decays continuously at a constant rate of 2.4% per year. So this is going to be my K value. It's going to be, since it is decaying, I'm going to use a negative 0.024, and that's going to come from this value. And so you can see that they've already placed that value into the function as K. Just wrapping it around in case they hadn't done that for you later. You can figure out the K value because it's decaying. You know, K is going to be negative, and you're going to use the percentage rate, the continuous growth or decay rate, to write your K value. Okay, so this is the formula for the number of strontium-90 after T years. Now, if 10 grams of strontium-90 are initially placed, so P sub 0 or P naught is going to be 10. Determine the number of grams present after 20 years. Okay, so I'm going to write my function P of t equals 10 times e to the negative 0.024 t, and then I'm going to find P of 20. All right, so we're finding P of 20 from that. First, I need my equation. P of t equals 10 times e to the, I gotta move my book out of the way. There we go. Negative 0.024 t. Okay, so P of 20 is going to be 6 and some change. So there used to be 10 grams initially, and then after 10 years, there's going to be 6.2, say, grams. Or 6.19 grams of strontium left, depending on what they need us for rounding. So we'll just go for 6.2 for right now. All right, onward. How long will it take for the given quantity to decay to 2 grams? We're going to solve this one by hand as well. So we're going to do 2 equals 10 times e to the negative 0.024 t. And you have to isolate your exponential, so we've got to divide off that 10 as our first step. So that gives us 0.2 equals e to the negative 0.24, I forgot a 0, 0.024 t. Okay, now again, I like to switch this with its inverse into logarithmic form. So I'm going to write a logarithm with a base of e. The logarithm with a base of e is the natural logarithm. So ln, I don't have to write the subscript. It's known that its base is e. Then the inside of the logarithm is the output. They're inverses, right? So the input of the logarithm is the output of the exponential and vice versa. The output of the logarithm is the input of the exponential. Okay, now I can evaluate the natural log of 0.2 Okay. So up here, I would have negative 1.61 equals negative 0.024 t. And then I can divide both sides by the negative 0.024 to get t by itself. So if I take this number, which I already have typed right here, and divide it by negative 0.024, that's going to give me 67.1 equals t. So that means that it will take 67.1 years for the initial amount to decay to 2 grams. To decay to 10 grams. To decay to 2 grams. From 10 grams down to 2 grams. 67.1 years to decay, my writing's a little smushed there, to decay to 2 grams. Okay, now let's check this one for fun. I never got rid of my old equations up here, so let me get rid of those so that I just have the stuff about this one, okay? So let's check this. This would be an output of 2, and if 67 is going to be a long ways to zoom out. So let me just pop my x-axis up to 100. I can click on the intersection point right there of 67.1 grams is what I had said. As you can see, 67.059, if I run into 2 places, would be 67.06. So we're on the same track here, rounding wise, for our solution. All right. And the last couple parts, we have how long will it take for the initial amount of strontium to decay to half its original size. So what we're trying to compute here is the half-life. So to compute the half-life, you want half of the initial value. The initial value is 10, so I can go ahead and plug in 5 because that's half of 10, half the initial value, times e to the negative 0.024t. The mechanics are going to work the same way as I did before. I'm just going to have a different number on this side once I finish my division. So divide by 10. That gives me 0.5 equals e to the negative 0.024t. Switch into inverses. Natural log 0.5 equals negative 0.024t. Evaluate the natural log of 0.5. That's just a number. Maybe I can write it down here. There we go. The natural log of 0.5 is negative 0.693 equals our negative 0.024t. Divide both sides by negative 0.024. I already have that number typed, so if I divide by negative 0.024, I get 28.9 equals t. So the half-life of strontium 90 is 28.9 years. I can check this graphically. Y equals 5, 28.9 years. Again, I could have kept more places. Because it's years, I didn't really think I needed them, so I only rounded to 1. Last, do you think the half-life of strontium is 29 years? Okay, 28.9, they rounded to a whole year, so they even rounded even more. So 29 years regardless of the initial output. So yeah, of course, because it's a constant. As we learned when we were doing half-life and doubling time earlier in cluster 1, for an exponential function, it doesn't matter if you're halving from 10 down to 5 or from 100 down to 50 or 20 down to 10, the half-life is going to be a constant. Yes, because the half-life of an exponential function is a constant.